All right, let's get right into it. Welcome to today's Explainer. We are diving into a really incredible journey today, starting from the deeply human philosophy of what actually makes our cities feel alive and traveling all the way down to a master mathematical formula that makes building those cities possible. We're going to connect the historical masterworks of classical architecture, the biological necessity of natural patterns, and the cutting-edge parametric software used to design the urban spaces of tomorrow. Basically, we're looking at a grand unified theory of fractal architecture. We're going to see how the brilliant work of Vera de Spinedel, Nico Salengeros, and even Frank Lloyd Wright all tie together into one single elegant equation. It's totally going to change how you look at the buildings around you.
So let's start with a feeling. I want you to intuitively compare two very different experiences. Imagine you're wandering through the winding cobblestone streets of a medieval European city, say Bruges or Rome. You immediately feel a sense of discovery, right? Comfort, vitality. Now, contrast that with walking through a sprawling modern industrial suburb, or maybe one of those vast, empty concrete plazas. It feels disjointed, cold, and frankly, kind of dead. Why is that? Well, it's not just nostalgia. It is literally math and biology. We are instinctively reacting to the underlying geometry of the spaces we inhabit, and that sets the emotional stakes for everything we're about to explore today.
Section 1. The need for fractal architecture. To really understand this, we have to look at the work of mathematician Nikos Salengeros. He, along with other visionary urban theorists, proposes that modern architecture is currently struggling with a massive crisis of scale. We've essentially forgotten how to build for human beings. See, for most of the 20th century, our built environment relied heavily on static, Euclidean geometry. We used simple rectangles, straight lines, mostly driven by repetition and economies of scale. It's highly isolated, it's integer dimensional. But natural living systems, they just don't build like that. Nature uses fractal patterns. Think of recursive hierarchies that repeat at multiple scales, like the branching of veins, the unfurling of a fern, or the jagged edge of a coastline. Fractal architecture is dynamic, it's biophilic, and it relies on multi-scale interactions. It builds a kind of complexity that our brains are naturally wired to understand and, honestly, to crave.
Salengeros refers to this necessary complexity as fractal loading, and this is such a brilliant concept. It means that in a healthy environment, you have dense, nested structural choices happening all at the exact same time, particularly at the human scale, so ranging from about 1 millimeter up to 10 meters. Imagine a traditional city street. You've got the grand scale of the building itself, the medium scale of a colonnade or a porch, the smaller scale of a doorway, all the way down to the intricate carved ornament on the door handle. This overlapping set of choices creates immense synergies for our psychological health, our local economics, and even resource conservation. When we ignore fractal loading, we end up creating what Salengeros bluntly calls catastrophically failing art products.
Section 2. Masterworks of geometric scaling. Now, visionary architects have actually always intuitively understood this need to build with fractal geometry, even way before computers made it easy to visualize. Take the plan for Frank Lloyd Wright's Palmer House in Michigan. He didn't just lay down a standard Euclidean grid, no. He took a single geometric module, an equilateral triangle, and repeated it on 7 different scales throughout the entire ground plan. It gives the Palmer House this remarkable, organic, and truly fractal organization. The parts reflect the whole, and the whole reflects the parts. Or, for a more striking modern example, look at Story Hall in Melbourne, designed by Ashton Raggett McDougall. That wild green and glass facade isn't just random shapes thrown together. It's a precisely fractal tiled surface inspired by Penrose tiling. The self-similarity of the panels, where smaller triangles create larger triangles of the exact same proportion, creates this incredible visual coherence and aesthetic richness. It's a mathematically precise way of reintroducing the detail and ornament that 20th century modernism completely stripped away. Section 3. The metallic means family. But here's the thing, to systematically replicate this natural beauty without just, guessing, designers needed a robust mathematical toolkit. And this brings us to the foundational work of Dr. Vera de Spinedel. She introduced what is known as the metallic means family. Essentially, these are special numbers carrying the names of metals that are born from generalized secondary Fibonacci sequences. What makes them so magical is that they are the absolute only positive quadratic irrational numbers that satisfy both arithmetic additive properties and geometric progressions at the exact same time. Okay, in plain English, they are the perfect mathematical bridge for scaling things up or down proportionally while keeping everything perfectly structurally locked together. Historically, you're probably already familiar with the golden mean, super famous in Greek architecture and, of course, championed by Le Corbusier. But there's also the silver mean, which was actually the basis for Roman systems of proportion. Then you have the bronze mean, the copper mean, the nickel mean, and so on. Each of these metals provides a completely unique ratio for scaling space that inherently maintains that beautiful, fractal self-similarity we've been talking about. However, there is a major core limitation here. While Dr. de Spinadel's metallic means are absolutely brilliant, they exist as isolated points. To jump from the golden ratio to the silver ratio is a discrete mathematical leap. So if you're an architect designing a building, you're basically forced to pick one of these rigid steps. You can't smoothly slide between them to micro-tune the spatial decay of your rooms or your plazas to fit the exact messy physical constraints of a real-world site. To build truly adaptive, modern parametric cities, we needed a unified bridge. Section 4. The Base Scale Breakthrough.
And here it is. This is the ultimate mathematical breakthrough we are exploring today, the missing link that finally unites historical fractal theories with our modern software capabilities. It's the normalized base scale formula. Basically, by taking the classic Pythagorean triangle and setting the base a to a constant of 1, the entire historical framework of fractal scaling, everything from Frank Lloyd Wright's geometry to Salengaris's biophilic design to Vera Diaz Spinadel's metallic means, is completely reduced down to one single independent variable, b. The output, d, represents the decay rate. Simply put, it tells you exactly how quickly a space spirals inward and gets smaller.
Let's look at what happens when we play with that single variable b, almost like a slider on a mixing board. If you set b to exactly 1, the formula spits out a decay rate of 0.4142, which is exactly the silver ratio used by the Romans. If you slide b down to 0.5, the result is 0.6180, the classical golden ratio. This single equation completely unifies all of those classical architectural proportions into one fluid continuous parameter. You can now dial in a b of 0.7 or 0.2, giving you arbitrary microtuning across an entire continuous spectrum. It's a total game changer. Visually, that decay rate, d, guarantees that as you nest architectural rooms or structural columns or even panels on a facade, they are going to scale perfectly in a squared spiral. It creates a gapless and overlap-free tessellation. Everything fits perfectly together, infinitely, no matter where you happen to set your b slider.
Section 5, Parametric Simplicity in CAD.
Because remember, this isn't just Blackboard math. This is exactly how we are programming the smart cities of the future. In 3D parametric modeling programs like Grasshopper, generating nested fractal geometry usually requires intense, highly complex 3D coordinate tracking. But by normalizing everything to this single variable, it's a total revolution for CAD fabrication. An architect can just sweep a single slider B to dynamically alter the entire spatial envelope of a building. The coordinate step sizes scale exactly by powers of the formula, meaning the math literally never breaks. It is incredibly efficient to integrate into Python scripts if you want to model entire modular neighborhoods.
And we're seeing this in actual VR architecture and visualization projects being developed right now. Designers are utilizing this exact math to create continuous, self-similar environments. The scaling is perfectly controlled by the base scale formula, resulting in digital and physical spaces that feel structurally infinite yet incredibly cohesive. And here is the practical payoff for an actual builder on a construction site. If you raise that decay rate to the power of n, which is just the number of spiral loops or nested rooms you're designing, you get d. D is the exact amount of open footprint remaining. So think about it. If an architect wants a central plaza or a building atrium to take up exactly 25% of the total footprint after 4 loops, they can instantly calculate exactly where to pour the concrete. All of it is derived directly from that single b offset.
Section 6. Building, Living, Sustainable Cities. As we wrap up, we really have to bring this explainer full circle. We've gone deep into the cold, beautiful mathematics of the base scale, but we must connect it back to the warmth of sustainable, biophilic living. The future of fractal urbanism is about so much more than just attention-getting aesthetic schemes. By using this math, we embrace economies of differentiation and adaptation, which is exactly how nature builds. We optimize material efficiency because the panels and beams tessellate perfectly without any waste. We achieve acoustic harmony, and most importantly, we restore scalar integrity, a state where the absolute smallest detail of a building intimately relates to the overarching scale of the city itself. This isn't a gimmick, guys. It is a structural necessity for healthy societies that actually resonate with human biology. The best part is, we don't even need to know the exact algebraic formula to appreciate this nested complexity. As human beings, we are very, very good at intuitively reading the multiple scales of these place networks. We literally feel it in our bones when an environment is mathematically harmonious and fractally loaded.
We finally have the parametric key to unlock the natural beauty of the metallic means in a continuous, fluid way. The mathematics are completely solved. The software is ready to go. The only thing left is a choice, and it's a question drawn directly from Nikos Salingaris' critique for all of us to ponder. Will we use this parametric key to return to living fractal cities that actually nourish the human spirit? Or will we remain trapped in the disordered geography of failing art products? Thank you so much for exploring this fascinating topic with me today.